It's not on.
Check. Yeah, this is better. It's my pleasure to introduce Zico Kolter. Zico is a world-leading expert on many of the safety issues that we talked here today. So this morning we talked a lot about GCG attack, and it's from Zico actually. He's currently the director of machine learning department at CMU, and also board member of OpenAI. So we probably will get to hear some hot takes as well. And Zico decided to use whiteboard to keep the spirit of Simmons. So this is going to be different.
Yeah. I can't do a whiteboard talk here when you're ever going to get to do it. So thanks, everyone. Thanks very much for coming here. I know I was probably invited here to talk about robustness and the kind of work I do here. I'm going to talk about a little bit different thing today. And it's actually submitted to archive this morning. So it's going to appear tonight, unless it's too hot for archive. That happens sometimes with our papers, and they're held back until someone approves them. But Tom approves them, right? Top Dietrich approves them. Something doesn't happen though, it'll be up tonight, but I'll actually put a website up at the end too, where you can look at a draft if you want to. But I won't put it up yet because it's going to also show the results. And I want to keep the suspense and see how well it works, which is not great, but it works interesting. I think it's a really interesting idea. Okay, so what I'm going to talk about today is I'm going to talk about just one topic. And I'm going to actually work through kind of what we're doing and what we're thinking about. And the topic is what we call anti-distillation sampling. And the idea is very simple. And by the way, I know that I can talk maybe philosophically if there's time at the end about why I think this is an actual, genuine, good idea. I know there are also skepticism around it, maybe. The idea here is you want to release models in a closed weight form that cannot be cloned by sort of other third parties. I think there are very good safety reasons for this, but I also acknowledge there are obviously competitive advantage reasons for this too. And so you have to take it kind of as you see for it. I genuinely am going to try to emphasize some of the safety applications here. I think it is a good thing if you can release closed models for a time before there's an open variant. I think it is a good thing broadly if you can release models that can't just be the capabilities immediately cloned by other third parties. But this is the world we live in is a complex one, and so I understand that there are positives and negatives of this. Okay, so the question I have kind of motivating this work, and to be fair, I'll just spoil the end here. This is not a perfect thing. It doesn't work perfectly, but I think it's an interesting idea, and what comes out of it is very interesting in a way as well. So the formal question here basically is, can I release a black box model that you can query where it does not benefit you to train on the generated data from this system? All right, so I'll just write this here because I'm going to try to keep up one board here. I won't write too much prose. I'll mainly be writing math, but I'm going to try to motivate this as the. So can I release a black box model where there's no benefit to training, distilling a student model on its samples? Now, this is a high-level question for the current time. Of course, what do I mean by benefit? What's the actual form? But I'll formalize all in a second. But that's the core question. Because right now, we do know that if you release a model, even without releasing the weights, even releasing it in a closed source fashion, people can query this model, generate a whole bunch of training data from those queries, and in many cases, replicate a lot of the functionality of the underlying model by doing that. This is true, of course, this is true if you have sort of full logits of the underlying model, but it's true even if you just have samples from the underlying model. This is still possible to do. Not perfect, but it still does work. And so I want to at least think about, and I think, again, I can talk about this more, but I think that this is not a great equilibrium to be in for a few reasons. I do believe fundamentally, I believe in open source models. All the experiments I'm going to show you are using open source models, but I think it is a very good thing that there's a gap between what closed source frontier models can be capable of and a similarly capable open source model from being released. Hopefully the point where if we see that there are truly scary capabilities coming out of models, which may happen relatively soon, we might really think whether we want to release this in an open source manner or not. So I think it's a good thing if we have this. Yes, Yashua.
Can you say a few words about the cost of that distillation? Like how would you get some useful?
Yeah, so in practice, you don't need too many, right? I mean, people distill these chain of thought kind of reasoning models with 1,000 examples of, generated chain of thought from the teacher model. It's usually very little data you need in order to sort of get this capability, and at least to a certain degree. And so I think it's, it's worth asking, can we sort of think about how to prevent this if we do want to prevent it? Okay, so let me formalize some of these notions right now. I'm going to start by assuming that we have what I'll call a teacher model. Think of this like a really big closed source model. So this is, I guess it was just released an hour and a half ago. So now we can talk about this being 03. I feel bad for everyone that was here during the talking during the release of the 03 live stream. And what this does is this model basically gets a distribution over next tokens, right? So it gets a distribution over some token t plus 1, given all the previous tokens. It's parameterized by some parameters, which we'll call theta t for the teacher. Now, typically, and of course, it does this for all of them. I'll use the notation here. I'm going to write it this time for now. I'll use the notation p dot to denote the entire distribution over all next tokens. And I'll put in a specific xt if I want the scalar probability value for a single next token. This is just for notational convenience. I'll kind of iterate between these two. Okay, so this is the teacher model. And typically what we do when we actually, of course, sample is we sample tokens, something like the following, right? We take xt plus 1, and we sample them, I shall even write it like this. We sample them according to some distribution, which is usually a scaled version of this. So we usually don't sample exactly from that. We use something like temperature scaling. So we sample it from some distribution like this, the log of, actually, I'll write it over tau. The log probability. Okay, so that's sort of normal sampling. Okay, and next we also, though, have a student model. And for now, I'm not gonna, I'll talk about it later in a second, but for now, let's not worry about sort of what the ultimate task of each model is. We'll just assume that this model, as it is, can solve some good problems. We just sample this, it solves some pretty hard math problems, things like this, right? We also, though, have a student model. And this is something, this is a model we have full access to the weight. So this is something like llama. Say it's like llama 7 billion, 8 billion, I guess. Llama 8 billion. Okay, and what we do with this model, and this model defines a similar distribution, right? We define a distribution of all next tokens given the current tokens, parameterized now by some parameters theta s for student. And what we will do if we're training this model based upon samples from this distribution here is we will get xt plus 1 given the teacher model. And then we're going to take a gradient step on the student model to update the parameters based upon that token. Now, of course, in practice, we do it in terms of mini batches, all that kind of stuff. But let's just conceptually think about if we sample one token, what we're going to do is we're going to update the student model based upon that one token, based upon updating the negative log likelihood of that one token. All right, so the update rule would be something like this. I'm kind of crouching over here, but it'll be all right. The update rule for the student would be something like our updated parameters of our model are going to equal the current parameters minus the gradient of our loss, right? And so this would be something, current student parameters minus the gradient of our loss. And our loss function, so minus some step size times the gradient of our loss. And this gradient would then be the gradient with respect to our student parameters of the negative log likelihood of this token given the previous tokens, right? So it's the negative log probability of xt plus 1 given x1t and the student parameters. Okay. Now for simplicity, I will just cancel these two negative signs and just have this. So this is our update. Okay. So that's how we would update the student based upon a sample from the teacher. And what we want to do is we want to pick, and obviously also, of course, in reality, you're not going to be running just one step of gradient descent. Both you're going to have many batches. You're probably going to have some other optimizer as well, but we can conceptually think of the updates kind of moving in that direction, right? Where this, again, this sample is sampled from the teacher, and we're taking a gradient step on the student. Now, I should actually, before I get any deeper here, I want to switch gears a bit and just make the point that in reality, we wouldn't actually know what someone's student architecture was, right? We wouldn't actually know what they're using to distill the model. And in this exact notation here, it actually only really makes sense if the tokens are the same across these two models, which doesn't necessarily, of course, hold if you're distilling arbitrary models. But so instead of using the term student, I'll actually use the term proxy, because we are going to assume we have kind of a smaller, typically smaller model that actually has the same tokenizer as the teacher model. This is, llama 7 billion with llama 405 billion as the teacher or something like that. But I want to emphasize that this is still a model that we have access to, and we're going to use it as we would a student. But then, of course, we're going to evaluate the final model in a setting where the proxy and the student are different models. So we want this process to generalize over models. Yeah.
How important was it that these 1,000 distillation samples came from another language model? Like if I just had a human emulate like the task and write 1,000 samples.
Yeah, so in general, those things have not been very successful. Trying to sort of, enumerate thinking was not as successful as just sampling from a reasoning model to get the thinking traces. But it's also a matter of volume. So 1,000 is a small number. That was this Stanford's S1 paper did this. But oftentimes you need more than that. So, but if you can generate them automatically from a model, you can get way more of this data, and that's much more effective, right? And the point still holds here, that you want to generate samples such that it is hard to distill a model. Yeah.
Wondering if you can give some motivation why distillation works with such a seemingly small number of examples between such large class differences?
Sure. I mean, I think the 1,000 example cases is an extreme example, and it probably means the base model could do reasoning already. It was just kind of needed to be kind of nudged in the right direction. That's the most likely scenario. I do think, though, that especially for larger sample sizes, it is definitely the case that you are giving new capabilities to the model. I mean, 50,000 really high quality traces of data is actually extremely valuable. You can really learn new skills in that. And I would actually argue, we learn all the time from really high quality, a textbook can teach us a lot, even if it's just, a relatively small number of tokens. So I think it's actually very possible for high quality data to learn a lot from the underlying, from relatively few tokens. But really, this actually applies, I would say, regardless of how many tokens you're talking about. Okay. So the last ingredient, I think actually is the last ingredient we need here. So I have the student model, but we're going to as I was talking there, I erased all the S's and wrote P's to emphasize it's a proxy model, not the actual student that we're gonna distill on. It's a proxy model. And the last thing we're gonna have, and maybe I will write that, I'll try to crouch down here and write that as well. So we're gonna have a downstream loss. I'm going to call this L, and this is going to be a function. It's going to be a function. We're going to think of it as a function of the student parameters, the proxy parameters, and it's going to be a mapping from this thing to the real, of course, just the positive reals. And the way to think about a downstream loss is think about it in terms of a validation loss on some large holdout set evaluating some task you care about. So I'll sort of say, again, this could be something like holdout loss on math problems. This is something, to be clear, it's not what we're going to finally evaluate this thing on, but some sort of holdout fine-tuning set that you might want to use on math problems, right? Sort of say, how well could the student model do on math problems, right? And these are the three ingredients that we have here. And what this means is we're going to evaluate the quality of the student using this downstream loss. Okay, we want to train. Now, when I say sort of no benefit, what I mean is we want to generate samples from our model such that when I train my student on those samples, it does not improve the downstream loss as it normally would if you sampled from normal samples. Okay, does that setting make sense to everyone? Sort of the setup here. Yeah.
In the end, the teacher model is producing outputs for humans.
Yes.
And I was wondering, like, if you take the proxy analogy as a human now, like, would the human find these outputs useful? Like, would the end, like,
we'll see some traces at the end. I'll come back to that question now. That's a good question, though. Yeah.
Presumably, if you change theta t,
yeah, so of course this is going to be a trade-off, right? So the presumption here is that theta, the teacher is pretty good at this downstream loss. And what we want to think about really is the trade-off between the quality of the teacher samples on this downstream loss or more conceptually kind of on actually solving some problems and the student quality on these problems. Yeah, that's right. Yeah.
Is there an assumption that the math problems at test time and the X's that you use at teacher sampling from the teacher, they are from the same distribution or similar?
I mean, I only in the very fuzzy sense of distribution we get with language models. These are not in any way from the same distribution. This loss here is not sampled from the teacher's outputs. Definitely not. This is some other set. It could be. I mean, that would be a reasonable set, but it does not have to be. It could be. And the way to think about this is it's holdout loss on math problems, but it's also large. So this is sort of it's a large downstream loss. Takes a while to compute. You have a whole lot of examples. There's a whole lot of large corpus here that you're going to use to evaluate the quality of this model. Yeah, Jeff.
Will paraphrasing break the method?
So again, you're evaluating the loss. So we're going to think of this loss as actually the log likelihood on some holdout corpus. So it doesn't have to generate, just has to have a high likelihood under the student model of that. And we're going to use that as a proxy. I mean, perplexity is a reasonable proxy for it.
Paraphrase them and train on those.
Oh, I mean, yeah, so maybe, but I think it's actually interesting. Well, I think what you will see in the samples will make it more interesting. I suspect it actually wouldn't help that much to paraphrase the answers. I think you get similar performance, but that's a good question. We could try that. This is all very preliminary, so yeah.
Do you consider the model collapse when you're generating those data?
Again, this happens all the time. People distill models all the time without model collapse. I think that's a separate issue. Yeah. Distillation works, to be blunt about it, right? We know it works.
Yeah, but for next generation of AI.
Yeah, but I'm more concerned about the current models and whether you can distill a current model into a smaller model typically. So let's go about solving this problem now, or at least proposing a solution to this. So what we're going to do is we're going to use what I'll call now anti-distillation sampling. And the idea is very simple. The idea is we're going to add an additional penalty, an additional essentially energy term in our teacher distribution to account for how much that sample would help a follow-on loss. Okay, so we're going to sample according to basically this following distribution. I'm going to write it like this. Try to be consistent here. Okay, so what we want to do is we want to write our, basically adjust our sampling distribution for each token such that we include the original likelihood of that token under the original model, plus some term that basically affects this thing, the term that depends on how much we adjust our downstream loss. All right, so here's the basic idea. We're going to sample xt plus 1 according to the following distribution. And I'm going to use now sort of, distribution for a single xt because that's going to be, a sample we then train on. And so it's going to be, according to this distribution, it's going to be the same as this one here, this one, temperature scaled version. So it's going to be exponential of tau times the log of the probability of xt plus 1, x1t under the teacher model, plus just some other term based basically upon how much the loss will decrease when we do that. All right, so I'll write this as basically lambda times the loss of theta plus the updated proxy model minus the loss of the updated, the original proxy model. Right? So this is just depending on your setting for lambda now. This is just going to trade off between making the likelihood high in our model and making the updated loss have higher loss than the original loss. So we're sort of going against the direction you'd want to typically go in the loss. We're making that loss higher. All right, so this one encourages sort of sampling, normal teacher distribution. And this one here encourages, and I'm not writing this in terms of xt plus 1, but of course this term here depends on the choice of xt plus 1. So this is a function of xt plus 1. And this encourages worse downstream loss when you train it, or when you distill it. Make sure my time is good here. Okay. All right, so that's the actual thing we're trying to do. But there's an obvious problem here, right? And the problem is, I just told you this loss is a really hard, long thing to evaluate, right? It's, a large corpus. And we have to do it now in, this naive way. We have to do it for every possible token. We'd have to, update our proxy model, evaluate this big complex loss for it, and, see how much it changes, and do that every single time we sample every single token. Obviously, it's not going to work, right? But that's the goal. And now what we basically show is that we can actually get extremely close to this very efficiently. All right, so now I'm going to talk about how we do this, the actual implementation. Okay. All right, so let's start off by defining actually a little bit more about this. I'm going to write this function delta basically as this difference here. So I'm going to write delta. I'm going to now make it clear that it actually depends on xt plus 1. I should actually also make sure that it depends on, maybe I'll, I think it isn't in the paper, but I'll write it like that just for now. So what this thing is this thing is defined as the loss of this guy. So theta, the proxy, plus eta times the gradient with respect to this thing of the log probability of xt plus 1 e theta e minus the loss, the original loss of theta p. Okay, so we're going to define just that delta like that. All right. And so again, we can just rewrite our sampling objective here as sampling this plus a little bit of our delta term. Yeah.
I'm trying to think about what's the right way to add in this other term.
Yeah, so actually, I would agree this is actually a pretty reasonable one. The reason why it's reasonable is, especially if this is an average cross entropy loss on some holdout set, it's actually the same kind of units as this. So these are in some sense comparable things. Obviously, if one is, a image reconstruction loss and something like that, and then it's less obvious. But I think this is actually a pretty reasonable thing. These are the same, again, a loss here, if it is a negative log likelihood on some holdout set, then it's actually pretty reasonable, I think, to use this as your loss, and to just trade off equally like this. And obviously, you want to evaluate this for a set of lambda, right? It's gonna require you to actually sort of, it's a hyperparameter. You got to test those different things. But I think it's actually pretty reasonable in terms of a way of parameterizing this. Okay, I'm curious if people have an idea where I'm going here or not, or if it's very unobvious, but we'll see. All right, so now the cool thing about this is, this is setting a specific eta there. What eta are we picking? Well, let's do the obvious thing and sort of take the increment, look as eta goes closer and closer to 0. And the other thing we can do is, because this thing is arbitrarily scaled, we can just arbitrarily scale lambda here too. What we can actually think about is think of this thing as taking the limit as eta goes to 0, and then also scaling it by 1 minus eta. All right, and when we do that, this thing here is actually just the definition of a derivative. All right, so let me write out what I mean by that. We can look at the limit, look at the limit as eta goes to 0 of 1 over eta of this thing. Oops, added drawing deltas because I draw nablas so often. Of delta xt plus 1 given e, and that's just equal to, apologies for drawing this out one more time, that'll be equal to the limit as eta goes to 0 of 1 over eta times, was this?
You can write gradient directly.
Oh, I don't know. Humor me, Joshua. Beta p plus eta p log t. I'll write faster. 1 to t p minus log. Okay. All right. So this thing, of course, as you were saying, what this is this is just a directional derivative of the gradient of this thing inner producted with that. All right. So in other words, this is equal to the inner product of the gradient with respect to the proxy parameters of our loss, beta p, and this term here. I don't need a, no, I do need a, there. Okay, so that's cool, right? Because now I can just compute this big expensive gradient of the loss one time at the beginning of my sampling procedure, and I never need to recompute it again, right? I just need to recompute the inner product of my likelihood term and this thing, or the gradient melody term and this thing for each sample. Okay, so that's nice. I can do that now, much more easily for each token. But it's still actually not that nice, because I would still naively at least have to do it for every single token. I have to recompute this thing, compute this gradient again for each token. Token number 1, token number 2. I have to compute this for every single possible loss term, or for every single possible next token. Compute the gradient, take the inner product. Okay, but if you're following, if you where I'm going at this, you probably have an idea what I might say next. What this term actually is for every xt here is actually a vector Jacobian product, but maybe more just concretely, what I can say is this little trick we applied here of going from sort of a limit here to an inner product of a gradient, we can do the exact same thing again, but instead of applying to this first term as we did here, we apply it to the next term. Okay, so I'm just going to write out what the expression is, and I'll try to, and this is actually the last one I really have, and then we're done. This is all the math. It's not that complicated actually, but it's fun to write out math on a whiteboard sometimes. Again, what better place for it, right? So this thing is also equal to, I'll give myself a little more space, would also be equal to the limit as epsilon goes to 0. Man, I write theta and nabla unavoidably when I write zeros sometimes. Goes to 0 of, okay, remember the trick here. To get a gradient, you take the function, plus a little bit of something minus the function at its original point. I can do the exact same thing to express this gradient here. Okay, so this thing is equal to the log probability of xt plus 1 given xt, or x1 to t, parameterized by theta p plus this update here, plus now epsilon, because this is, this update here, epsilon times this guy. No, I didn't let myself enough space. Sorry, let me rewrite it. I want to have this all in one line. This whole thing is equal to limit epsilon goes to 0 of 1 over epsilon times log p of xt plus 1 given x1 to t and theta p plus a little bit of this guy plus epsilon times this one. All right, minus the log probability of this thing at its original point. So this would be xt plus 1 given x1 to t, parameterized by theta p. Okay, does everyone see that how that worked? Basically, I just used a directional kind of directional derivative to express this limit as an inner product of the gradients, and I just undid that trick, not with the first term, but with the second term to express it again as a limit. All right, but the cool thing is now, this is just the output of the model. It's the output of two different proxy models. One proxy model where you sort of add a little bit of the gradient with respect to your downstream loss, and then the original proxy model. And you can compute that importantly now for all next tokens simultaneously using just two forward passes in your proxy model. You can also do it, by the way, with a vector Jacobian product. That does work, but then you have to run it in AutoGrad and all that kind of stuff. It's just more annoying. It's much nicer, and getting the precision and stuff is much more annoying here. It's much nicer to do it with finite differencing, as we found. Okay, so maybe to summarize here, I'm gonna maybe use one more board. I think I'm messing up all these boards here. Yes. Is that going to be confusing? Yeah, it's going to be out of order now.
All right.
It's all right. All right. All right. Jeff, yeah.
Say I succeed in doing that.
Yes.
And I make every gradient step do the opposite of training the functional model for good.
Yes.
And I just use the negative steps to get a good model. Or
Well,
like so-
let's talk about that actually. That's very interesting. Actually, you'd think so, but it doesn't actually work. It's very weird, but we'll talk about it.
one, but
Yeah, we can talk about it. So in theory, yes, but in practice, it doesn't actually work. It actually works it still works badly. We'll get to that. I think if you actually do that, you would really screw up your model. If you take negative gradient steps always, yeah, that would really mess up your model pretty well. Because again, it's still a trade-off between these two.
There's a convexity issue.
There's some broader space of
The final tokens won't, I mean, if you had just the tokens sorted according to this, you could do it. But ultimately, you're getting samples that mix these two things together. And you have to have a fair amount of a real teacher in there. If you take negative distillation steps, you're going to completely nerf your
I
model.
think I'm more concerned if you like have Carlini spend a month trying to undo this method.
Yeah, I mean, I'm sure there are ways to get around it. This is more a conceptual sort of presentation than anything else. Probably, yeah. I mean, also see how well it works. It's debatable whether you want to do this, but I think it's still getting at something really interesting. All right, so what's our real implementation look like? Let me just finally state the final thing. So this is the final algorithm. So to initialize, I would compute one time my downstream loss on basically the gradient of my downstream loss for my proxy model. So I compute, call it G, that would be equal to the gradient of my proxy model on the downstream loss. Then, for t equals, I guess, like t0, etc. Where t0 is my starting point, the things before that are the prompt. I just repeat two steps. First, I compute a approximation to this thing simultaneously for all next tokens. So what I do is I compute, I'll call it delta hat of xt. I'm going to run out of space here, I know. Hopefully I just mean it's going to be the finite difference approximation here. It's not exactly this because I'm going to have a finite epsilon. All the xt plus 1 tokens, yes. Sure, good point. Thank you, Yashua. x1 to t. Okay. I'm going to compute this now just as the finite difference approximation of that. It's going to be 1 over some epsilon naught, some approximation, so, some fixed number here of I'm going to run out of space here again, but I'll write small. Hopefully everyone knows what it is. It's just that thing I'm writing again. Log probability of dots. Maybe the dots will save me. 1 to t beta plus epsilon beta p plus epsilon g. Minus log dot of x1 to t of theta p. Okay, so that is my finite difference, I guess epsilon naught. That is my finite difference approximation to this penalty term for all tokens simultaneously. It requires 2 forward passes of the proxy model to compute. Yeah.
You said you wanted to create well downstream losses, but in the end you do manipulations and you get this delta to or delta hat.
Yeah.
Say, oh, I wanna, as originally my problem is to sample according to the probability plus this delta.
I think this makes much less sense to me as a ration. I mean, it is the same thing, so it obviously is the same. I think this as a motivation makes way more sense about the objective than specifying this is the objective to me.
I mean, you could interpret this as you want the token to be less likely after the dates.
So, yeah, but again, what is the, so you're saying that you would update, you know, this update again is the update of a downstream evaluation loss. You wouldn't actually carry out that update in practice. This is the one you carry out in practice. And they're only equivalent because of this manipulation here. So I think it's important to emphasize that.
But in practice, you don't, in your algorithm, you don't need the second term after the minus because it's going to be a constant in the softmax.
This term here?
Yeah.
Why would it be a constant in the softmax? No, it's still for every, this is the original model. It still is it still is for different for each token. Yeah. Okay, and then now we just sample C+1. Sample it according to our original distribution, this mixture up there. Hot. Teacher plus lambda times this thing. That's it. Wish I could have gotten it on two boards. I should have crouched down. Oh well. Okay, that's the algorithm. Let's see how it works. Any questions before I do that? Yeah.
So what's the conceptually succinct way of stating how you got around the problem of you have to do this intractable computation to do this kind of sampling originally?
Yeah.
Some small manipulations and then you're good now.
I mean, I think this is the beauty sometimes of math, right? These things actually are equivalent. So in the limit of small step sizes and small updates to your model, these two things are in fact mathematically the same. Right? They are the same direction. And so what it really is that there is just what's conceptually how you can compute the Fourier transform to multiply matrices in n log n time or matrix vector multiplication by n log n time. It's a mathematical transformation that does in fact save you effort here.
Is the approximation just the update isn't?
I mean, I think that so look, in general with these things, like what it's saying in some sense is that the direction you would update it in, because you would, I mean, in some sense, yes, because you are not taking that large step, you can approximate kind of the direction, this loss, right? You can approximate sort of the loss of your, the update loss here as the inner product of these two gradients. Okay, nice, it may be hard to see how to go. You can approximate this thing, right? This thing here, as the inner product of two gradients. That's just sort of numerically what this update means as you are going smaller and smaller in your step size. And then similarly, what this means is that you can approximate the same thing via a kind of weird update you would never do in practice to updating your model in the direction of some downstream evaluation loss. And that's, I mean, I think that's just kind of interesting. Those actually end up being equivalent. It's funny because it used to be that all machine learning papers did this, right? The thing you would always do in a machine learning paper is you would propose some really complex algorithm and you would come up with an efficient approximation, and that would be your actual algorithm. It's less common in LLMs, I'll admit, but I mean, I think this is sort of standard tricks, to be honest. Yeah.
I have a slightly higher level conceptual.
Sure.
Because we're living in a discrete space, right?
Yes.
They're kind of flip with some probability, we flip the token of the output.
Sure.
And then we'll try to flip it at a given time in such a way that it's kind of adversarial.
Yes.
A lot There's nothing here to make sure that this is imperceptible, right? Like, we could just
Oh,
make
no. So it's definitely not, I'll show them, it's definitely not imperceptible. I mean, if you have, so I guess, okay, good point. There's absolutely nothing to sort of, I mean, this can just completely destroy the actual tokens you're sampling from. I mean, for a large enough lambda, you will just sample the worst possible token, which is not going to have any actual semantic coherence, right? It's going to be just the worst possible token always. What I will show you is that for tokens in, for lambda in the middle, it does interesting things, is the way I'll put it. Yeah.
I think that one of the applications is you want to so that you have the local minima for the proxy.
Yep.
But in practice, you want to.
Well, no, it doesn't mean you're a local optima. I mean, so actually, why are you saying that?
Because the loss is worse.
Yeah, but it could still be going. So this loss was like they're both going down. They're like the loss. This is like you're here on your loss curve, and then you're going to move to here. And I don't want to move to there. I want to move to up here, something like that. This update here does not require you to actually be at a minimum for it to make sense, I would argue.
But okay, and my second question is, you want to protect yourself from against many proxy models.
Yes, so this is very empirical. And so what I'm saying is we're going to use a proxy model to generate strings, and then we will empirically evaluate how well this transfers to other models, including other tokenizers, all that kind of stuff. And to be clear, we actually have very sort of, we have relatively sparse results so far, but I'll show you these hints that what we do is our teacher is a Quen reasoning trained model, reasoning distilled model. Our proxy is another Quen model, and the student is a llama model. So we're going to try to actually then use these traces to train a llama model in here.
If you do a gradient descent step, you have to.
What? Why? No, I don't understand.
Beta plus is a gradient descent step.
Yeah. Yeah, so this would say you're going to take my next set of parameters is my current parameters minus a step in the direction here. This will update the parameters. If you're a local optima, this will be 0, so it wouldn't matter. These have to be different for it to make sense, in fact. Yeah. Either one, yeah. Yes, you back, in the back. Yes, you can go.
So you emphasized at the beginning that it's a held out loss.
Yes.
What sense is it held out?
Okay, right. So what I mean by held out is we're going to evaluate the final reasoning performance of this model just on other problems that were not directly in this downstream loss. And I'm not even going to evaluate it in terms of a loss function, because this loss, again, is cross-entry loss. All I just mean is that, if we use like GSM-8K as traces from GSM-8K from a reasoning model as, the likelihood of those traces as my downstream loss, I don't want to evaluate my performance on those exact same problems, because that could just sort of, screw up those problems, right? We want to know, is there some fundamental kind of quality of the model is actually being lost here? All right, maybe I'll show the results, and then they're not as earth-shattering as maybe I've hyped it up to be, but at least it's still. What was that? I can just write it on the whiteboard. I know, yeah. It's unfortunately that would be cool if I did. Yeah, I'm gonna do this first. Giving away the answers here. Let me actually do separate monitors. Without giving things. All right. So let me show you what this looks like. First of all, let me show you a separate plot. With this separate, and I'll just take some time talking about this. So this separate plot, so this is, that I've described here, one way of perturbing the sampling update to make it worse. You could also just increase the temperature a whole lot, make it much more random. That's also going to be really bad at generating good samples for distillation. And so what matters is not the fact that it works. Yes, we know we can just generate samples that will screw things up. That's not a problem. What matters is what's the relative trade-off of how well the teacher works, because that's sort of what you want, versus how well a distilled student works. Okay, so we're showing here, and it's going to be, we're going to have one result here. These take a while for us to train, so we're have limited resources here. We're releasing an initial version with just these results. This is GSM 8K. The recipe here is that we have a teacher model. This teacher model, actually, I should put it on the plot. The teacher model is Quen 7 billion distilled from R1. So R1 is a reasoning model. You can create distilled versions of this. You know, they are much better at GSM 8K than a standard base model will be. And they're good at solving these problems. In fact, when you sample them normally with just sort of zero temperature there, you get about 90% accuracy for the teacher. Arguably, actually, what matters sort of most is this top left corner. I'm actually not going to focus on that here. I think that's kind of things we were looking at in the future. Let's sort of consider the case where you actually were willing to sort of sacrifice a reasonable amount of accuracy to just disrupt your sampling procedure or the distillation procedure. All right, so this is what temperature scaling looks like, and it's not very good. And the reason why it's not very good is that if I have sufficient noise in my samples to make my teacher have 50% accuracy on GSM 8K, there are just some basic math problems, then I still actually, by distilling those samples, I can still get my student to be pretty good. My student's almost 50% there. In fact, to make it noisy enough where it no longer is useful, you have to actually decrease the accuracy of the teacher below what the student has to begin with when you do this. So temperature sampling does not solve this problem. You can't just make noisier samples. Even when the samples are, have a little bit of information in them, it seems like students can kind of glean some content from this in a meaningful way. All right, now I get to do the reveal. So, this would be the worst possible sort of Pareto frontier here. And the optimal Pareto frontier would just look like a straight line down, right? And then maybe go over or something like that. Okay. This dotted line here, by the way, is where the student's accuracy is undistilled. So if we just start with a student that's there, you can train to a point where the student actually does worse, to be clear. But it takes a long time and a really bad model from temperature scaled sampling. All right, and whether this is a good result or not, I'm not sure, but this is the result. This is anti-distillation sampling. So the take home here is, for example, if you are willing to tolerate 70% accuracy for the teacher, then you wind up getting a student that actually works worse than the original student, despite the fact that this is definitely sort of non-negligible performance on this benchmark task. And what maybe arguably matters is sort of more this range here. That's why I kind of don't like the shape of this curve. I was hoping to do like this, but the world is the world, unfortunately. But around here, these are also reasonable points here, because what these are saying is, with a 10% drop in accuracy, I can create a student that still is not bad. It still is reasonable. But if I distill the student, with uncorrupted data, I get these points up here. And that is quite a bit better. The student will get 60% accuracy. If I'm willing to tolerate, a little drop, I can make the student get 45% accuracy instead. I think all these points are actually kind of interesting on the plot here in terms of kind of the trade-off that they imply. Yeah.
This accuracy number is exactly the thing you put in the sampling.
No. So this accuracy is actual solutions on GSM 8K, where you sort of give it an answer and you have a verifier that checks accuracy. This is the real downstream loss we care about. The L there was a likelihood on other held out GSM 8K problems generated by a good reasoning model. It's a little bit convoluted, I'm aware, but the thing is, this accuracy here is not differentiable in any meaningful sense. This is just you ask for the answer in a certain form, you check with a verifier if it gets that. This is what really matters about these models. This is what everyone actually checks with them. So I think it's the more important thing to show, but it's not the actual downstream loss that we optimize on, no. Yeah.
The very top left, it's kind of hard to see, but is there any case where, like, I'm guessing in the cases where it's better, your teacher is better?
I think actually what happened here is, oh, I see. So not really. I think this point here is just the greedy point. So we didn't actually, the reason why these blue dots don't quite get there is we actually stopped temperature sampling at some level. We didn't go all the way to 0. The lambda equals 0, and we actually do greedy sampling with lambda because it's just more deterministic that way. That one is, I believe, the top point. So I think the best point you can do is to actually have just no lambda at all. I didn't see any sort of better student performance. We did, by the way, initially, maybe this was a question you were alluding to here. We tried to look at anti-distillation sampling, which was, can you actually flip the sign and just make it do better? Unfortunately, it doesn't actually do better. I was really hoping it would. You come up with this sort of magical distillation that, you know, magically makes your things better. It didn't do it, unfortunately. Yeah. Let's see. Go there. Yeah.
Are there any universal anti-distillation strategies that are robust against different models?
No, I mean, I think, look, this is, to be clear, the student model is a different model than the proxy model and the teacher model. So in some sense, you are actually creating samples that are just uniformly worse to distill on in weird ways, the same way that there's sort of weird transfer across models and attacks, adversarial attacks in general. In a way we don't really understand. I think that's what you're seeing here too.
Yeah.
I'll show you the traces in a second too. Those are also fun to look at.
But
Yeah.
you need to know your target model class or the proxy model class in order for
the proxy. Yeah, but you just pick the proxy. The proxy model you pick. The student model, the actual student model, you don't know. But you have to pick a proxy to carry this out. Yes.
Yeah. Do you have any sense of what these curves would look like if you double the number of samples?
No, but we're running those experiments now. You will know what they are in a few months. Yeah, or a few weeks. Weeks, I think, hopefully, depending how much money we have. Yeah.
Get the challenge that there is a in terms of capacity to this model?
That's a good question. We haven't done a lot of work with using the same capacity model. I think in this case, the models are the distilled 7 billion. I would bet if you had all 7 billion models, you'd have the same kind of effects here, because distilling from Quen distilled is not as good as distilling from the original R1, right? And the real, I think honestly, the bottleneck here is our distillation process, which is not as good as the full distillation process you run on the larger, they use to create our teacher model in the first place. So I think it's much less about capacity, much more about just the amount of data you have and things like this. Yeah. Yeah.
I'm considering as you're keep querying the teacher model, every step you get some non-zero positive information gain from the teacher model, right? So as you're accumulating, I'm considering the anti-distillation as time goes on may not be very optimistic. And in that sense, could you find something from an information theoretical point of view as Shannon's channel-wide that guaranteeing as time goes on, you're actually learning from the teacher model?
I mean, I think that's very hard, right? Especially when you start talking about not just increasing. I mean, this is all generalization upon generalization we're talking about here, right? So this is sort of generalization of this particular loss function, this particular update to other samples, and then the effect that has on not just this downstream loss, but the actual problem-solving ability of the model. I think it's very hard to sort of give guarantees about that chain of generalization processes. Not that it's impossible, but it would be interesting, but we haven't done that. What I will say, just as an initial, maybe also to your question, is that this does seem to actually get a little bit better as you add more data, as you create larger and larger data sets for sampling here. So I don't think it's a matter of just sort of pruning out information from them. Really, if you do that, if you only have a few samples, you just will never get that good performance. The performance will never improve that much. So this line here will just all move down. So the fact that you retain this sort of pattern as you push this line up here, i.e. as you add more and more data, is still encouraging. Now, whether in the limit of infinite data, this line kind of converges upward, it's hard to say. This might be why you have that little pattern there, but I'm just speculating here. It's hard. I'm almost certainly over indexing on a few little results here. All right, I think we're almost out of time. Maybe before we go, or we are out of time. Before I go, I want to show some traces. So here's what they look like. Oops, let me go. Okay. Here are what anti-distillation traces look like. Let me make it bigger. Okay. This website, by the way, antidistillation.com, you can get the paper there. Basically, this is for when you get 80% teacher accuracy. So that is here on the plot. So still pretty good, still pretty useful answers. They look okay. They look kind of interesting. They look like reasonable sort of thinking strategies. They're not always sort of 100% correct. They do weird things sometimes, like have text after the thinking and stuff like this, but it kind of works. So it does a lot of thinking first, and then it's after the fact solves the problem and stuff like that, but it kind of works. What I think is really interesting is as you go down. So as you go down it doesn't actually, it's not very hidden. What it does is it creates basically adversarial examples in your traces. And so just naturally what you get are things like this. So this is solving a math problem about, charging for houses. And it thinks for a while and it says, XML RPC, fiber, Aldo drinks fiber. I'm sorry, I'm not to help with painting charges. He is painting and doesn't know how much he charges there. Then it stops thinking and then outputs the answer kind of outside the thinking. So it's really weird. But importantly, this is quite a bit better than it's still 70% accuracy here. It's still doing quite a bit better than a non-reasoning model at all does on this same problem. Okay, yeah. So this is absolutely true, and so it's actually an interesting lesson, right? Because I think we started out this project, and this is the last thing I'll say, and then we'll adjourn. Though I'm happy to keep talking. We started this project thinking about this would be a nice way to show traces to people, to show thinking traces in a way that was not actually going to reveal information, and would still be a good thing. What we found, in fact, is that actually this is a very interesting way of obscuring the traces themselves. It still seems to convey information. So this is kind of a weird one here, but some of them in the thinking, they do some amount of, this one's interesting. This does kind of actually carries out the calculation correctly in the thinking, but then generates a bunch of XML, ends thinking, and then ends the answer. What seems to be happening is that what you actually get from this is you get sort of injections of weird attacks into the thinking process in a way that makes them, if you train on this, very bad, and maybe obscures some of the reasoning itself, but which still arrives at the right answer. That's kind of weird. I don't know what to make of that. Maybe this is a good thing and maybe not. Maybe this is a good way to analyze nonsensical chain of thought, because you're generating answers that sort of maximally try to disrupt the usefulness of the chain of thought in some sense, while in other cases not doing anything. So I don't know. And I think it's a reasonable question what the utility of this is. But I think I'm going to wrap up here, and then I'm around for a while. Come ask the questions if you have a chance. But thanks everyone for listening.
Lunchtime.
Yeah. How does this relate to the other work at OpenAI on chain of thought, association? So I guess it's what Davis is doing.
I think in the end it might be doing